I forgot to check. It's not obvious if there's going to be a quiz on this chapter because it's linked to the next chapter, right? What quiz are you guys working on?
Finished them all.
What number?
Six.
Quiz 6.
So this is on chapter 9.
Yeah.
Center
All right, I got to check. I got a feeling there is a quiz on this. I think that kind of break we had was the only. There's more quizzes in this class than I'd like to do. But
Yes, more than I like to.
Okay, so before we look at these problems, I just want to mention here, this came up yesterday in that demonstration with the spokes, with a different, where you could apply the force, the hanging weight at different radiuses. And a lot of people fall for this, and I have too. It's natural to think that you've got this, you're driving this with this weight here. If you double the radius, you would think that you would double the torque, right? I've fallen for that. And I think this is what the issue that came up yesterday. But it's not true. The reason it's not true is this tension here is not constant. The tension here, it's not static. It's not m times g. It depends upon the acceleration. So you have to solve this problem, and you can also, we know enough now to solve it, okay? But I just wanted to mention here that because the tension is not constant, then the torque is not proportional to R. Therefore, alpha and A are not proportional to R. However, if it's accelerating slowly, if A is much less than G, then the tension is approximately mg, and then the torque will be proportional to the radius. So if you're interested in this, come by and see me. Okay, so let's look at first problem here. This is one of the, the conceptual, we have a couple of conceptual questions, right? So here's what we're given. There's no gravity here, incidentally, right? You don't see a G. If you want to think of this, you can think of it as the top view of this rod on a, being with some axle here off center. So we have a constant force here. We have this other force here, F2, whose the magnitude is constant, but the direction can be different values here. So the first thing you want to notice is both of these torques are in the same direction. Does everyone see that? It's physically clear because the torque due to F1 is going to cause rotation, counterclockwise rotation, and so is that, okay? And if you do the R cross F thing, you're going to get that they're in the same direction. Okay, and it's also physically clear. The maximum angular acceleration is going to occur for which of these three values of the force of F2 here? The 90-degree one, because you're going to get the biggest torque, right? And they threw a little twist in here. How does the angular acceleration, we don't have to worry about it. This is constant, so we don't have to worry about that. And it's contributing in the same direction. These two here, you'll notice here that 70 degrees is 20 degrees less than 90, right? And 110 degrees is 20 degrees greater than 90. So both of these have the same torque. The reason is that the torque here is this distance times the projection, times the projection of the force in this direction. In other words, the tangential component of the force. Both of these have the same tangential component of the force because they're same angle. This angle is the same as that angle. So you're going to get the same torque. Remember, all that's important in the torque here is this tangential component. The radial component does not contribute, does not do anything to the angular acceleration, obviously. Question? Was there a question? Oh, I thought I saw. Okay? So, we have the same angular acceleration for 70 and 110. I don't know why you guys are looking at me this way. This is pretty simple, right? Yeah, make sure you get this. This is basic, this is conceptual question type stuff, right? quantitative. Any questions about it? Okay, the next one is, oh yeah, this one. Okay, so these are composite discs, okay? They all have the same radius, these two radiuses here, and this radius separates material of different density. The darker part here is a denser material, and of course it's uniform. The material is uniform here, it's uniform here, but the density is greater there than here. You can imagine that, right? And we're given these three different situations with a force of common magnitude applied at the outer radius here, and then here it's done here on the inner that inner radius. Is that clear? So we're supposed to. This is one of their ranking. They love these ranking problems, right? I'm gonna rank here. The first is the torque. Which problem is this? 10. Okay, yeah. So we're going to rank the torques about the axis. Okay. These two torques are the same. Same force, same distance. Torque's going to be the same. This torque, because it's the same force, will be less. Okay, so the ranking is going to be like this. Torque 1 and 2 are equal, and they're greater than torque 3. Okay, what about moment of inertia about the axis? What's the ranking there? Well, the first thing you want to look at here is these have the same moment of inertia, the same body, here and here. Now, how is that moment of inertia going to compare to this one? And this, again, this is physical. Right? You don't want to think formulas when you're. We got they all have the same mass, right? But what's the difference between this and this? Effectively, the mass has been moved in. It's been moved from here to there. So when I move the mass, when I got an object and I move mass closer to the axis, what happens to the moment of inertia? It gets less. It's easier to rotate. When you apply torque, you're going to get a greater angular acceleration. If all the mass were concentrated at the axis here, what's the moment of inertia? Yeah, it's going to be hard to be very close to zero. So a little bit of torque and boom, it's rotating. Okay, so moment of inertia ranking. These are the same, and they're going to be greater than this. And finally now, the angular accelerations. So we want to rank these. So so you can do this in different ways. We can compare. There's different routes you can get to the answer here. Let's look at these two. What has a greater angular acceleration? This one, because it has less moment of inertia. So the angular acceleration of this will be greater than the angular acceleration of this. And now it's natural to compare these two. What's the angular, how are the angular accelerations going to compare here? Well, they got the same moment of inertia, but we reduced the torque. So this will have greater angular acceleration than that. So that nails down the ranking. Okay. Any question? You know, if there's any questions, especially about these conceptual problems, you need to come by and talk. I need to know, right? It's kind of late in the course to say this, but these are things that you want to physically feel. Typically, these conceptual questions. That's their purpose. Okay, so this is a classic. We have a clock, like that kind of clock, right? Not a digital readout type clock. Did you know that there are people these days who don't know how to read a clock? I was amazed. One of my brothers teaches in a state I'm not going to name, and He teaches like high school equivalency courses, you know, for older people who never got a high school degree. And he told me, he says, oh yeah, there's a lot of, they can't read a clock.
Are they blind?
No, I don't know. They're not blind. But you guys are aware of that. Some of you are aware of that. Somebody said,
It's not even the younger generation. I had a woman older than me look at my watch and say she couldn't tell time on it.
yeah, well, my brother, he has older people, you know, people that never got a degree from high school, so they tend to be older. Yeah, it was amazing, you know, we take things for granted and just, Okay, so, the second hand, you can see it there. That's the one that we can clearly see moving. It has an angular velocity of so many radians per second. What is that? What's the omega value? Well, it completes one revolution, which is 2 pi radians in 60 seconds. So it's 0.10, you punch this in, it's 0.105 radians per second. All right, what about the minute hand? Well, the minute hand, it takes, it does 2 pi radians. There are different ways of doing this, but I think this is probably the easiest. It goes around once, 2 pi radians, and how long? 1 hour, right? Or 60 minutes. So I'm going to get rid of the minutes. I can do the simple conversion here, right? Multiply by 1. I choose this to be to represent 1, because then I convert it to radians per second, and I get this, it's milliradians per second. It's slow for us. Well, finally, the hour hand. The hour hand takes how long to go around once? 12 hours. So it's 2 pi radians in 12 hours. And now we convert, 1 hour has 60 minutes, and there's 60 seconds in a minute, so there's the conversion factor. Here's the conversion factor. And I get, you know, roughly 1/10 of a milliradian per second. Any questions about that one? Okay, so this is a rotational kinematics, or kinematical type problem. We're not going to talk about dynamics here. This is just, it's analogous to the one-dimensional kinematics we did, straight line kinematics we did a long time ago. So the information we're given here is that we have this flywheel. It turns through 40 revolutions, and it's decelerating, and it's got a constant negative angular acceleration. And it goes through, it starts at some initial angular velocity, 1.5 radians per second, and it comes to rest 40 revolutions later. So I tend to do a graph here. We don't really have to use this graph. We can just launch into the equations, but it's usually helpful to draw something, you know, something pictorial, okay? So here's omega versus t. This is a straight line because it's constant angular acceleration, negative acceleration. Starts it here at time t is equal to 0, comes to rest at some time we're not told, and it takes 40 revolutions. And I know that if you integrate the area under this line here, the area of this triangle is going to be 40 revolutions. And it's directly analogous to the fact, the one-dimensional motion case, where for constant for any motion, the displacement is the area under the velocity versus time curve, right? So that's why I wrote it there. So in this problem, it's best, and then it's happened before, I think it's best, there's always different ways of solving these problems. I think it's best to do part B first. We're not given any time information here. And we're asked a lot of questions, so we're going to have to find the angular. It's obvious that we're going to have to find the angular acceleration. So, and once we do that, it'll all be simple. So, I think it's best to do B first, and because we're not given any time information, we use the no time equation. So we know everything here except alpha. The final angular velocity is 0. The angular displacement here, or we can set theta 0 equal to 0. We're free to do that. but this is the angular displacement. It's 40 revolutions. Now, that's not the SI units here. We got to convert this to radians. In one revolution, there are 2 pi radians, so this converts it to radians, this factor of 1, and I multiply it and I get that number of radians, 251 radians. So I use the no time equation to find alpha, and the negative sign correctly comes in here, and I get this value. All right, so now let's answer the other questions. What time does it take? What's this final time where it eventually comes to rest? Well, we can get that just simply from the fact that omega is varying linearly in time, because we know alpha now. So the final omega is 0, just solve for this. And even the signs work out, right? This is not a negative time because alpha is negative, all works out. And we get a certain time here. Now, the interesting part about this problem, I think, is C here. How much time is required for this disc here, this flywheel, to complete half of the 40 revolutions? Okay, it completes, this is 40 revolutions from here to here coming to rest. What's the time it takes? And it's going to be somewhere right around here. It's not going to be halfway, is it? Why is it not? Why is the time to complete 20 revolutions not halfway?
It's slowing from its angular speed.
Yeah, you're on the right track. The easiest way to see it is, remember, the displacement's the area under this curve. So I got to set these two areas equal, so it's going to be over here. But you're right. You know, it's moving much faster here than it is down here. So that's going to push it from the halfway point here over there. So one way to do this is to use the third equation. We have these 3 equations that we use for constant acceleration, whether it's linear acceleration or angular acceleration. And here it is. All that's important is the display. We can set theta 0 equals to 0, as I mentioned before. And we know everything here. We're going to specify theta to be 20 revolutions now, which is 126 radians. And we know everything except the time. So we can find the time. However, we get a quadratic equation. So here I put the quadratic equation in standard form and written out the numbers. And we can say, and you guys all know the quadratic, how to solve the quadratic equation, right? So I thought it'd be nice once in this course, I don't think we've done this before, to solve the quadratic equation, okay? And it's actually kind of interesting, and let me explain. So when you solve this, you're going to get 2 solutions, because it's quadratic equation. Typically you get 2 solutions. Sometimes you get no solutions, you know, they could be complex, they couldn't get real. We get 2 real solutions here. So which one is it? Which one's correct? Well, look at the time here. We've solved for the time. It's 335 seconds. Clearly it has to be less than that. So we got to rule out this 572 second solution. So this is the answer. Okay? But why did it give us this? Do we just throw it away, saying, oh, it's not right? No, usually when this happens in physics, this is a solution to the problem. We've asked for the time it takes to go 20 revolutions. And almost always, and we're getting a solution, it's going to correspond to something real. Can anybody think of what's happening here, what it corresponds to? Here's a hint. We're just doing math here, right? Does the math know that the flywheel stops at this time? Nope. What the math knows is that we have this constant angular acceleration. It's just, this line's just going to keep going. It doesn't know that. We haven't told it that. That's part of our interpretation. So now you tell me, let me help out. Okay, you tell me, what does that big time correspond to here? It's going to be over here, because here the flywheel stops.
Would that be a second?
And then it starts going in the opposite direction. So it's made the 40 revolutions. Now it's going backwards. There's going to be a point of time in which it's gone a net of 20 revolutions, and that's the time. So it does correspond to something physical here. Now, there's one more thing I need to say about this problem. You can avoid the quadratic equation, and I should have written this down, okay? And I'll let you think about this, and if you're interested, you can come by and talk to me. By looking at our two other equations here and solving for some intermediate quantity, you can avoid the quadratic equation, and then you'll be restricted to here, and I think you'll just get this answer. But I feel I need to say that you don't have to use the deal with the quadratic equation here. Okay, any questions or comments? But I think it's interesting here. This happens a lot. It's good not just to chuck a solution that you think is not physical. It usually corresponds to something, and we see what it is in this case. Okay, 20. Oh, this is a centrifuge problem. Okay, 10-meter radius, and the centrifuge here, the angle is given by this relationship here. And again, if you just saw this, you would know that there's something wrong here because the units don't work out right. This is dimensionless and radians. We have seconds squared. Something's wrong here. So it's fixed by this statement right here that this holds. This is true for t in seconds and theta in radians. You need to be told that. Something like that. So we can find the angular velocity. It's d theta dt, just like the straight line velocity is dx dt. And we get, it's easy to differentiate, we're going to get 0.60 t. And again, this doesn't make sense, but you have to add, I'm assuming this, right? And finally, and then next we get the angular acceleration, which is d omega dt, and this is a constant. And I should have written this in here. We want to make sure you understand, this is a constant. And we know it's going to be because this is quadratic. So this is a constant angular acceleration problem or system here. So we're asked that what happens at 5 seconds. The instantaneous angular velocity, which is increasing in time, at 5 seconds it's going to have the instantaneous value of 3 radians per second. I just substitute 5 in here. The velocity of the person here on the rim is increasing in time, okay, because it's v is equal to omega r. This is a standard relationship that we use a lot. And it's just going to be this omega times r, which is 10 in SI units, 10 meters. So we get 30 meters per second. That's the instantaneous velocity. The tangential acceleration we get, this is the speed. It's omega times r. We differentiate this with respect to time, and that gives us the tangential acceleration, how the speed is changing. So this is going to be alpha times r, because we just differentiate this with respect to time. And we know alpha here. Alpha is a constant, so we get this. And this is a constant, the tangent. While this thing is increasing its rotational rate, in a regular way, it's varying linearly with time here. The tangential acceleration is a constant at 6 meters per second squared. Finally, the centripetal acceleration, this person's going in a circle here. At any moment, there's going to be a centripetal acceleration because there's a force. Because the person's moving in a circle, there has to be a force here. So in this case, remember it's v squared over r, but the better way to think of it is omega squared r. There's 2 ways we can think about it because they're clearly equivalent. So instead of v squared over r here, we're going to use, in rotational problems like this, it's better to use omega squared r. We know omega squared, we substitute it in, we know r, and we get 90 meters per second squared. So that's roughly 9 Gs, right? Which we know from Mitch is a lot, right? Okay, any questions about that one? Hey, the next one here is a kind of a classic problem. They ask a lot of different parts. We're just going to focus on, I think, what's interesting here in this problem. So that's part B. So we have a turntable, which maybe some of you have seen, and they've actually come back in fashion a little bit, right? Analog recordings. So it's this, you play records with this thing. But it's this table that's rotating at a constant angular velocity. And this is the, for the standard records, LPs, which stands for long playing, which you may not know, it's 33 1/3 revolutions per minute. That's the standard speed for a turntable, okay? I still have a turntable. It's in the garage, and I think I put some plastic over it because it just keeps picking up a lot of dust. But I say, well, you never know. I might need it sometime. Anybody have a turntable here? All right, Aaron
Beach Boys album,
and
the house
Gene.
that I'm renting has a turntable built into the house, and it still works. This, the system in the house still works, so it plays throughout the house. I just need a Beach Boys album.
Wow. Yeah, right. Yeah.
Or it could go.
Has anyone seen that new movie about Brian Wilson? His documentary? I think it's the documentary. What?
Seen the trailers for it. I know what you're talking about.
Oh. Yeah, I'm thinking of, I'm thinking maybe I should look at that. I don't know. Never mind. Okay. So anyway, we have this disk rotating at a constant angular velocity, and it's equal to this. And this is what they really rotate at. Okay? The ones that still work. And here's the idea. We have a mass on here, and there's some static frictional, some coefficient of static friction there. You put a mass on there, it could slide off, or the static frictional force could be enough to keep it going in uniform circular motion. So there's a critical case, right? There's going to be a critical case where it's just barely stays on the turntable. And by that I mean if you increase this the slightest amount, it's going to go off, right? That's what I mean by barely here. So in this problem, we're going to find the perspective here is we're given a certain radius here that this thing is at. What is the minimum coefficient of static friction required to barely keep it on the turntable, going around in uniform circular motion? Okay? So that may sound a little confusing to you, but it gets all cleared up when you start. Remember, force, there's the picture, here's the force diagram. So we have this mass, there's a normal force, there's gravity, and then there's this static frictional force, and we're going to max it out. We're going to use the maximum value, which is mu s times n, as we've seen before many times. So Newton's second law here is that the net force, which is mu s n, is the mass times the acceleration. And the acceleration here you want to think of, you can think of it as v squared over r, but it's natural, as I just said in the previous problem, to think of this as omega squared r, which is equivalent to v squared over r. So, and we know omega here. So I set this equal. This is going to give me the critical case. This is going to give me the minimum coefficient of friction, static friction, required to keep this thing on the table. I set these two things equal. It's independent of the mass. Mass scales out. And I'm going to get the minimum coefficient of friction. And you can see that it's omega squared r divided by g. So we need to substitute those quantities in. And now this is not in radians per second. This is valid. This has to be radians in, SI units. It's going to be radians per second. So everything's in SI units here except this omega. And I'm going to convert this. 1 revolution is 2 pi radians. We've done some similar before. I want to get rid of the minutes. So 1 minute is 60 seconds. So I punch this in and I get a value, 0.075 in this case. Remember, it's dimensionless. The coefficients of friction are dimensionless. Okay, any questions about that one? Okay, moment of inertia. So this is 41. So here we have, there's a perspective drawing in the book I'm going to do you a projection one. So you want to think of this. Here's the axis. It's coming out like this, right? And we have this uniform rectangle here. The mass is distributed uniformly here. And we want to find the moment of inertia about this corner right here. Oh, incidentally, how does the moment of inertia about here, how does it compare to the moment of inertia about here? I never thought of this before. Anyone? Yeah, who said that? Yeah, they're the same. They don't look the same. You have to actually stop and think about it a little bit. But it doesn't matter. You're going to have the same moment of inertia anywhere here. And one way of seeing that is as this thing rotates around, you know, it rotates around. At one point in time, it's going to be over like this, right? Which is the same as saying, using this and saying that the axis is here. So it's going to be the same. It doesn't depend upon what point you are there. So how do we calculate that? Or how do we find it? Well, the purpose, and I don't think you're told here, but if you look at the table, all these introductory mechanics books have tables of moments of inertia, and ours does too. You'll look in there, you'll find the moment of inertia about the center of mass. There's an expression for that, and here it is. Okay, now we can use the parallel axis theorem to find out what the moment of inertia is here, because we know the moment of inertia about this axis. We can find the moment of inertia about any parallel axis, no matter where, very simply from the parallel axis theorem that we derived in lecture. So I'm going to do this. I'm not going to plug the numbers until the end here, and you'll see why. I plug in what we get from the table here. And now I add mh squared. Now this h is this distance right here, but we can get that from Pythagoras, right? This is going to be the square root of this squared plus that squared. So I've substituted that in there, and it gets squared, so it's going to be this. And now I substitute the known moment of inertia about the center of mass, and we can simplify this. A 12th plus a 4th is a 3rd, and we get this. Okay, can we check this with something we know? Can we check this? This is true for any A and any B, any values of A and B. So what if we shrink A to 0? What do we have? But we still have mass. You know, I want you to imagine there's still mass here, uniform. We have a rod. We usually call it a rod. We know the moment of inertia of a rod about an N. It's 1/3 m times the square of the length. And sure enough, if you set A equal to 0, we get that. That's the right answer. So it works out in that case. Finally, you can plug the numbers in for our actual dimensions here, and you get some value there. Incidentally, I should mention here, at one point in lecture, the first thing we did was we actually found the moment of inertia about the center here. And I warned you it was for a thin rod, right? Because we treat it as a one-dimensional problem. When you have mass that's distributed like this, each little mass element, it's not going to be this. It's not going to be this distance. You're going to have to add this distance, so you get a greater moment of inertia if this thing is spread out. And this quantifies it. So if we had, this would be, for a thin rod, we would get this. When the mass is spread out transverse to the original rod, the moment of inertia is greater. We argued qualitatively that that has to be the case. And this is that's the quantitative result. Any questions about that one? Okay, 43. Okay, so this has been entertained. I remember hearing about it when I was a kid, okay? And it's, there's probably people still working on it. You can store energy in a flywheel, and then you can get that energy back. So the people have actually thought about utilizing this in vehicles. Now there's a problem with that, and I'm sure I will discuss it. And there's a related demonstration when we do the next chapter. There's a problem you have to, you could have a very serious problem if you don't recognize something here in utilizing this energy for a vehicle. And we'll talk about that in the next chapter. For right now, let's just say we have this, let's look at the problem. We have this heavy 500 kilogram cylinder or disc, uniform disc. It's 1 meter in radius, okay? Oh, they didn't give us the height. Does that matter? It's not going to matter. Okay? Remember, the moment, it's not going to change the moment of inertia. And we're given omega. Now this may look unusual to you. You might say, well, why didn't they just multiply it by pi? Well, they're doing this because often in cases like this, people don't like to deal with radians per second. In fact, you know, I don't like to deal with radians per second. I like to deal with frequency, right? So in cases like this, that could be measured in hertz. A hertz is one cycle or one revolution per second. Or it's very common to use, as we've already seen, RPM, right? Revolutions per minute. So they're doing this because if you convert it to RPMs, in the way that the simple way we've discussed, you get 6,000 RPM. And that's a lot of RPM. As some of you may know, like, typical automobile, I don't know if they reach 6,000 RPM. I don't really know. I'll bet someone here knows.
Yes.
Okay.
It's not good for them.
But it's not, you don't want to run it for any extended time, right? And another thing is that 6,000 RPM may not, for a relatively small object, it may not be that bad. The stresses aren't going to be that bad. But as you get to bigger and bigger objects, okay, something moving at 6,000 RPM like that, as I go to a bigger object, what is the speed of the rim here? It's going to get bigger and bigger, right? If I double the radius, it's going to double the speed. The stresses are going to go up to keep this thing intact, so it won't fly apart. Okay, and eventually, if you rotate it fast enough, anything will fly apart. You'll break it. Okay, so this is 1 meter here. This is serious. Okay, you would want to check to make sure that whatever material you're using here, or whatever, it's not going to be just one. You're going to have other things on here. You want to make sure that nothing's going to fly apart. Okay, so what's the kinetic energy here? How much energy is here? Well, it's just 1/2 I omega squared. This is a uniform disk, so it has a moment of inertia 1/2 mr squared. And we know omega, it's 200 pi radians per second. I substitute this in here, okay, punch it in, and I get about 50 megajoules. Okay, what's a megajoule? Well, it's a million joules, but how do we appreciate that? Well, that's the purpose of the second part of the problem here, I think. The power is the rate of change of energy with respect to time. Change in energy over change in time. This is we're going to imagine this is let me look at this. I just realized a problem here. So we're dealing with average power, okay? So the average power is the total change in energy over the total change in time. Okay, and that's why I didn't put the deltas. This is going to be the total energy. So we're given the power, the average power. We can find how much time it's going to, and we know how much energy we have, initial energy we have. We can find out how much time this will work to power the vehicle. How much time. That's a useful quantity. So we just solve this for t. So it's going to be the energy divided by the power. And you can see that the units work out here, right? This is energy per unit time. So this is all in SI units. I plug these in, punch them in. It means it's going to be seconds. And then that's a lot of seconds, so we divide by 60 to get minutes, and that's still a lot of minutes, so you divide by 60 again, and then we get about a couple hours, which is impressive. But there are drawbacks, right? You're going to be driving around with this heavy mass. And there's another real serious one, dramatic, that we'll discuss in the next week. Okay, any questions about this one? Okay, this, I don't know if you're going to believe this, but this system actually has someone's name attached to it. Oh, you have the copy. Okay, yeah, it's called an Atwoods machine. So you might think, somebody's name is attached to this? Well, how can that be? Well, historically, it was used, I think, to accurately determine the acceleration due to gravity. And the idea here is this. It's not easy to determine the acceleration due to gravity directly, right? Like think experiment 1, all right? But if we can slow it down somehow, then that would be good. So that's why that led Galileo to roll objects down an inclined plane. But typical Galileo, he introduced the complication here. Things are rolling. We still don't know how to solve that. That's next chapter, okay? But he somehow squeaked by. I don't know. He knew. He knew that something rolling down was not going to be the same as something sliding without friction. I'm sure he knew. Okay. But do you see what can happen here? What if these two masses differ by a small amount? What's going to happen? Suppose M2 is a little bit bigger than M1. It's going to accelerate, right? And it's going to accelerate very slowly. It gives you plenty of time to accurately determine G. But of course, there's a price you have to pay. And what is it? Friction. You got to make sure. So that's trade-off. It's a trade-off. So anyway, you can use this to determine G, but what I want to make sure I get across right now is, and that's the purpose of this problem, you can also use it to determine I, and the moment of inertia. And that can be useful, as I think I mentioned yesterday. Some objects are very typical, real objects that rotate have a very complicated geometry. And it can be difficult to accurately determine the moment of inertia. And in fact, you would have to, like I said yesterday, I think, you have to put it on a computer. You can determine it experimentally, however, and this is one way of doing it, because we know G. So knowing G, we can do it. And that's the whole purpose of this problem. So here's the information we're given. This mass, this release from rest, the system's release from rest, you'll do the final experiment will involve something like this. That's next week, next Friday, right? Not this Friday, next Friday?
Yes.
Okay. So we're given the distance that it falls released from rest, so I can, and we're given the time, we're given the distance and the time, okay, which easily can be measured accurately. Because this is assuming this is slow. And look at this. See what the authors have chosen? See how these are close? That's the slow idea. So we can find the acceleration of this mass. What's the acceleration of this mass? It's the same, just in the opposite direction, right? So from the acceleration, I can find the tension. And you're asked to do this in steps here. I can find the tension here. Because the force diagram for this is I've got M2G down and an impeding tension force up here. That has to be by Newton's second law, the mass times the acceleration. So I can find T2. And to three figures, this is what I get. All right. What about T1? Well, we can do the same thing with T1, similar force diagram. These have flipped because they're going in opposite directions. All right. So here's the net force. Mass times the acceleration. I know everything here. I can find T1, and I get a different tension. And why? Is this a mistake here?
No, that's that friction you were talking about, isn't it?
I'm sorry, did you say friction?
Friction that you're talking about?
This is friction-free. There's no friction here. We're neglecting friction and air resistance. This is we're idealizing the motion here, and it can be a good approximation, as you will find out. If you've got a decent ball bearing, you know, some decent bearings in here, and these things aren't moving very fast, you don't have to worry about air drag. This can be a very good approximation. So the math here, the physics, and embodied in the math here, or vice versa, I don't know.
Difference in masses?
It's the rotation of the wheel.
Yeah. The only way you can angularly accelerate this thing is you've got to have a torque. Where's that torque going to come from? If these two tensions are the same, you've got no torque. So they have to be different. So what the math has given us here is we've put in an acceleration. It knows that. It knows this wheel is accelerating. There has to be a net torque, and that's why it's returned us these different values. In fact, not only are they different, but which one's bigger? And T2 has to be bigger because we got to have the disc. The disc has to rotate this way. So this torque has to beat out that torque. Okay, we can get an angular acceleration is A over R. Remember, because there's no slipping of the cord. We talked about that yesterday. Remember, because there's no slipping, this cord has a velocity. At any instant time, it has a velocity, some speed, right? A point on the disk has to have that same speed. Otherwise, there'd be slipping. So that allows us to use V is equal to omega R. And then we differentiate that and we get what alpha is. So we can now find alpha. And now finally, from Newton's second law for rotations about a fixed axis, we now know everything here. We know the net torque. Well, we can get the net torque from the tensions. And we know the angular acceleration. We can find the moment of inertia. So that's our perspective on this. We're using the Atwoods machine here to find the moment of inertia. So no matter how complicated this object is, as long as the force is being applied at some radius here, you can imagine this to be some kind of wheel attached to some arbitrary object. As long as the center of mass is in the center, okay, otherwise we got trouble. But as long as it's, we won't have constant angular acceleration. But as long as it's balanced here, we can determine the moment of inertia no matter how complicated the object is. And here's how we get it. We take the torque, which is R times T2. There's competition in the torques here. That's the net torque, divided by alpha, and we get a number. Okay, any questions about that one? It's a good problem. Next is the famous H problem. This became popular last summer when I taught this course, and I can't remember why it became popular. There's something interesting here. You know, every class is different, and things happen. Anyway, here's the problem. We have this, and I didn't draw it quite to scale here. We have these 3 rods. They all have the same length and the same mass. So this is 1 rod, this is 2 rods, this is a 3 rod. I should have drawn this a little bigger, okay? But they all have the same mass, the same length. We're not told the mass, but that's going to drop out. It's not going to be important, as we'll see. And I think we are actually given the length. Yeah. So this is an H. It's a rigid H. And it's pivoted about one of the vertical arms of the H here. Okay, so imagine this to be a top view. You're looking down and you see this H. And it's released from rest horizontally, and it's going to fall down, and right at the bottom there'll be an angular velocity, the maximum angular velocity when it reaches the bottom. The purpose of this problem is to find that angular velocity. So here's a side view. So here's one arm. Here's the cross arm of the H. This one's over here, and it's going down like this. It's released from rest here and goes down there. So we want to find the final angular velocity when it's right at the moment it's at the bottom. That's the problem here. Is the angular acceleration constant here? Is the torque constant? There's a gravitational torque. You can imagine all the mass to be concentrated at the center mass. There's a torque. So what happens as it goes down? What's this torque compared to that torque? It's less. What's the torque here? Zero. Yeah, this is not constant angular acceleration. So that's telling you something right there. You can't use constant angular acceleration formulas. Well, we can use energy conservation, right? As you now know, and that's easy to use here. I'm going to call this y equals 0. When the center of mass is here, the initial case. So that means our initial energy is 0. That's okay. Nothing wrong with that. The energy is going to have, the mechanical energy has to be constant here. The kinetic energy plus the potential energy has to be constant. So the initial energy is 0. What's the final energy? Let's write down an expression for the final energy. That's going to be right at the moment it's at the bottom. There's going to be some kinetic energy, 1/2 I omega squared. And now what's the potential energy when the thing's at the moment it's at the bottom? Remember center of mass theorem here. We can imagine all the mass to be concentrated at the center of mass, and we just need to find the potential energy of a mass here where this is 0 potential energy. Well, it's mgh, but it's negative because it's down below here. If it were up here, it would be positive potential energy. This is negative. So it's minus mg times L over 2 because the center of mass is right there in the geometric center. So that's the important part of this problem here. That's probably the gives you the most trouble here is this. You got to make sure you recognize that. From now, it's straightforward. We're going to set the energy, these two energies equal, and then solve for omega. But we got a little bit of a problem. What's the moment of inertia of an h? Well, first of all, you can't answer that question. Why? What's the moment of inertia of an h? Don't look at this diagram. I have to specify the axis. Okay, trick question. So this is the axis, right? So what's the moment of inertia of h about one of the vertical arms here? Okay, it's the sum of the individual moments of inertia. What's the moment of inertia of this?
0.
Essentially 0. Very extremely close to 0. Negligible. That's the word. So we don't worry about that. What's the moment of inertia of this?
It's proportional to L.
Okay, that's right. So make the final step. You're there, you're almost there.
L over 2.
Now it's at a distance. I can imagine all this mass to be concentrated at a point here. I'm not changing the distance to the axis. So what's the moment of inertia of something, of a point? It's the mass times the square of the distance. So the moment of inertia of this rod is going to be ml squared. Right? And finally, what's the moment of inertia? We just talked about that. 1/3 ml squared. So we get 4/3 ml squared here. So this is another interesting part of the problem here. And the center of mass, the total mass, is 3m. So all that appears in here, here's the total mass right there. So there's a number of details here that you have to recognize. It's a good problem. But once you get through that, then it's just energy. We use energy conservation, and we can find the final angular velocity. Okay, any questions about that one? Damn. Okay.